One day, the universe as we understand it will come to an end. And nearly 30 years ago, scientists reached what seemed like a solid consensus on how that ending would unfold. Over unimaginable spans of time, trillions of years, galaxies would slowly drift farther and farther apart. Stars would burn through their fuel, cool down, and eventually fade into darkness. Black holes would gradually lose mass and evaporate until nothing remained but an endless, frozen ocean of empty space, cold, silent. This scenario is known as the Big Freeze, driven by dark energy. It arises from the accelerating expansion of the universe and has long been considered the most likely fate of everything that exists, or at least that's what we believed. Recent, groundbreaking observations from the dark energy spectroscopic instrument, known as DESI, are beginning to tell a very different story. According to these findings, the mysterious force we call dark energy may not be as constant as we once assumed. Its influence on the universe could actually be weakening, but what would that mean? If this is true, if the cosmic engine powering the expansion of the universe is starting to lose strength, then the ultimate fate of the cosmos is no longer certain. Everything hangs in the balance. In this video, we'll explore this potential shift in our understanding of the universe and examine why dark energy might be running out of power. Are our cosmological models fundamentally flawed? Or is there another explanation waiting to be uncovered? To understand how we got here, we need to rewind the clock to 1998. By then, scientists already knew that the universe was expanding, a discovery first made nearly 70 years earlier by Edwin Hubble. What remained uncertain was the exact speed of that expansion. Many researchers even believed it might eventually slow down. After all, it seemed logical. Gravity pulls matter together, so over time, shouldn't it counteract the expansion? The key to answering this question lay in determining the Hubble constant, a value that describes how fast the universe is expanding today. There are two primary ways to measure it. One by analyzing patterns in the cosmic microwave background, and another by observing the redshift of distant objects. Interestingly, these two methods don't agree with each other, a mystery known as the Hubble tension. Now we'll focus on the redshift approach. Traditionally, astronomers used Cepheid variable stars for these measurements, but Type Ia supernovae turned out to be just as reliable, if not more so. And without realizing it, scientists studying these colossal stellar explosions were standing on the edge of a revolutionary discovery, the discovery of dark energy. We know how intrinsic bright Type Ia supernovae are because they explode in nearly identical ways. Thermonuclear detonation of white dwarf stars locked in binary systems. By comparing their true brightness with how faint they appear from Earth, we can accurately determine their distance. Then, by measuring their redshift, how much their light has been stretched as it traveled through expanding space, we can calculate how fast they're moving away from us. This tells us how rapidly the universe was expanding at the time their light was emitted. Simple enough, or so it seemed. When two independent research teams analyzed data from more than 50 Type Ia supernovae, they noticed something unexpected. The supernovae appeared dimmer than they should have been at first glance. That might not sound remarkable, but it turned out to be a scientific bombshell team led by Sol Perlmutter, Brian Schmidt, and Adam Rees realized that these distant supernovae were fainter because they were farther away than predicted, and that could only mean one thing. The expansion of the universe wasn't slowing down, it was accelerating. Some unknown force was actively pushing galaxies apart. To visualize this, imagine drawing dots on the surface of a deflated balloon. As you inflate it, every dot moves away from every other dot, not because they're moving on the surface, but because the surface itself is expanding in all directions. What is dark energy? This astonishing discovery raised far more questions than it answered. The biggest one being, what is causing this acceleration? To this day, the honest answer is we don't know. Scientists gave the phenomenon a name, dark energy. Most believe it is an intrinsic property of space itself. The energy of the vacuum. Others suggest it could be a mysterious energy field permeating the universe, or a strange cosmic fluid, or even defects in space-time. Thin, one-dimensional structures known as cosmic strings, and some researchers propose something even more radical, that dark energy isn't real at all, but instead a sign that our understanding of general relativity breaks down when applied to the universe on its largest scales, and that the problem might be solved without the need for dark energy at all. But whatever dark energy turns out to be, or not be, it remains one of the deepest mysteries in modern physics. Inseparably linked to the accelerating expansion of the universe, the discovery was so profound that, following the 1998 results, the three astronomers who led the research, Adam Rees, Sol Perlmutter, and Brian Schmidt, were awarded the Nobel Prize in Physics for their groundbreaking work, the Standard Model of Cosmology. The revelation of dark energy led directly to the creation of a new cosmological framework, the lambda-cold dark matter model, commonly known as lambda CDM. The term lambda comes from the Greek letter used to represent the cosmological constant, first introduced by Einstein. It now serves as the mathematical description of dark energy within the model. The remaining letters CDM stand for cold dark matter. Together, these components form what is now considered the Standard Model of Cosmology. It provides the mathematical foundation for our understanding of the universe from the moment of the Big Bang through its evolution and all the way to its ultimate fate, including everything that happens in between. For several decades, lambda CDM has been the most widely accepted and most precise model we have for describing the large-scale behavior of the cosmos. Despite the similar names, dark matter and dark energy are completely different phenomena. Term dark is simply used to describe two separate things that we still don't fully understand. Dark energy is the force responsible for driving the universe's accelerating expansion. Dark matter, on the other hand, refers to a form of matter that does not interact with the electromagnetic field. It doesn't emit light, absorb light, or reflect light. In fact, it doesn't interact with light at all, and yet we know it exists. We can detect dark matter through its gravitational influence on galaxies and cosmic structures. The word cold in cold dark matter simply means that this matter carries very little energy, since temperature can be thought of as a measure of the energy of particles. But if dark energy and dark matter make up the entire name of the lambda cold dark matter model, where does everything else fit in? What about all the matter and radiation that we can actually see? Although it's not mentioned in the name, it is fully included within the model itself. All visible matter and radiation, including stars, planets, gas, and light, fall under the category known as baryonic matter. Using a wide range of independent measurements and observations, scientists have reached a remarkable consensus. According to the Standard Model, roughly 68% of the universe consists of dark energy, this mysterious fundamental property of space-time that we barely understand. Only about 5% is made up of visible baryonic matter, while the remaining 27% is dark matter. Let that truly sink in. Nearly 68% of the entire universe is composed of something we cannot directly observe and do not yet understand. However, there is a crucial assumption at the heart of this Standard Model. The value of lambda dark energy is assumed to be constant. Almost every cosmological calculation depends on this single assumption. It tells us that the expansion of the universe is not just continuing, but accelerating, and that it will keep accelerating forever, and that, as a result, the universe is destined for a cold and lonely end. Galaxies will continue to drift farther and farther apart as the fabric of space itself stretches outward. Stars will eventually exhaust their fuel, fade away, and cool into darkness. All the heat and energy in the universe will be diluted across unimaginable distances until the universe's temperature settles just barely above absolute zero, culminating in what astronomers call the Big Freeze. But what if we're wrong? For the first time since the discovery of dark energy, scientists may have identified one of its fundamental properties, and it's not what anyone expected. Dark energy is changing. In 2024, the Dark Energy Survey released the largest single collection of supernova data ever assembled, analyzing the explosive deaths of more than 1,500 stars. At first glance, the results appeared to support the long-held assumption that dark energy is constant. However, when this data was combined with other observations, including measurements of the cosmic microwave background and earlier galaxy surveys, something didn't quite fit. The numbers refused to line up. It began to appear that dark energy might not be constant after all, but instead could be evolving over time. If dark energy was changing, then our understanding of the universe would have to change with it. While the results were intriguing, they came with significant uncertainties, meaning they fell far short of definitive proof. To uncover the truth, astronomers needed a much larger and more precise map of the universe, one capable of testing whether this signal was real. And for that, they turned to DESI, mounted on their 4-meter Male telescope in Arizona. The Dark Energy Spectroscopic Instrument is mapping the optical spectra of tens of millions of galaxies and quasars, spanning billions of years of cosmic history. Its goal is simple, yet profound: to determine whether dark energy is truly constant. By capturing light from 5,000 galaxies at the same time, DESI is measuring the positions and recession speeds of roughly 40 million galaxies, allowing scientists to reconstruct the expansion history of the universe over the past 11 billion years. This is a massive international collaboration involving more than 900 researchers from over 70 institutions across the globe. In 2025, the first major datasets were released, covering the initial 3 years of the survey, with 2 more years of observations still to come. And what those early results revealed was nothing short of astonishing. Using data from nearly 15 million galaxies, DESI constructed the largest three-dimensional map of the universe ever created. This map allows us to move through a cosmic landscape containing millions of galaxies, each one home to between 200 and 300 billion stars. In this visualization, Earth sits at the center, and every single dot represents an entire galaxy. Blue points indicate galaxies farther away, while white marks those closer to us. The result is a universe so densely packed with galaxies that it's almost impossible to comprehend. With this immense dataset, astronomers measured baryon acoustic oscillations, or BAOs, across more than 40 million galaxies and quasars. BAOs are the fossilized remnants of sound waves that rippled through the early universe. By tracking how the scale of these oscillations changes over cosmic time, scientists can precisely determine how fast the universe was expanding at different points in its history. In these visualizations, the lighter blue regions represent sound waves traveling through the hot, dense cosmic plasma of the early universe. As the universe expanded and cooled, these tiny variations froze into place, leaving behind slightly denser regions of matter. Over hundreds of millions of years, those regions pulled in more and more material, eventually forming stars, galaxies, and the vast structure we see today. These ancient sound waves are still visible, etched into the universe itself as the vast interconnected network known as the cosmic web. The researchers then combined the DESI data with other crucial measurements, including the faint afterglow of the universe's birth known as the cosmic microwave background, the redshifts of distant supernovae, and weak gravitational lensing, which reveals how light from faraway galaxies is warped by the gravitational pull of matter along its path. And what they discovered only strengthened the findings from 2024. It appears that dark energy's influence is not only shifting but may actually be decreasing over time. In fact, their analysis suggests that the cosmic push from dark energy may have weakened by roughly 10% over the past 4.5 billion years. You can think of it like a car still moving forward with its foot on the gas, but gradually easing off the pedal. The vehicle is still accelerating, but not as fast as it once was. Similarly, the universe continues to expand, and this expansion is still accelerating, but slightly less rapidly than it did billions of years ago. If dark energy is truly evolving rather than remaining constant, then our standard model of cosmology is missing something fundamental and something enormous: the Big Crunch. If this potentially paradigm-shattering discovery is correct, it could point to a dramatically different fate for the cosmos. Rather than the universe continuing to expand forever into a cold, dark, lonely Big Freeze, we might face an alternative scenario entirely. If dark energy continues to weaken over time, eventually reversing to become negative, the expansion of the universe could slow, stop, and even reverse. Instead of drifting apart forever, all matter and energy could be drawn back together, culminating in a violent, universe-wide collapse. Picture the raw power of the Big Bang exploding outward with such force, energy, and heat that it created all the stars, galaxies, and cosmic structures we see today. Now imagine that force flipped completely in reverse. Everything rushing inward, converging on a single point, unraveling all that ever existed in one cataclysmic, universe-ending event, known as the Big Crunch. I've previously discussed the possibility of a Big Crunch, along with other theories exploring how physics might behave at the ultimate end of time. If you want a deeper dive, now, if dark energy truly evolves over time, the implications go far beyond the distant fate of the universe. It suggests that our current cosmological model is incomplete. It could mean general relativity, the theory describing gravity, may need revisions, and it opens the door to entirely new physics, potentially involving unknown fields, forces, or particles we have yet to discover. But before we start rewriting the textbooks, we have to be absolutely certain, and right now we're getting close, but we're not there yet. In physics, sigma, or standard deviation, is how scientists quantify confidence. The higher the sigma, the less likely a result is due to random chance. In the search for evolving dark energy, these sigma levels have been steadily climbing by itself. DESI data reaches just above 2 sigma, which corresponds to roughly 95% confidence. Interesting, yes, but nothing you stake your career on. Combine DESI with other instruments and the confidence rises past 3 sigma, even approaching 4.2 sigma in certain combinations. Roughly 99.997% confidence. This is considered strong evidence, meaning the results are unlikely to be a statistical fluke, yet it still falls short of the level physicists require for a definitive discovery. History has shown that results at this confidence level can still turn out to be wrong. So scientists prefer to wait for even clearer confirmation. Gold standard in physics is 5 sigma or 99.99994% confidence. And even then, errors are not impossible. For example, in 2011, researchers at the Gran Sasso laboratory in Italy measured neutrinos apparently arriving a few nanoseconds early, which, if true, would have meant these particles traveled faster than light, breaking the ultimate cosmic speed limit. They reported a confidence of 6 sigma, surpassing the gold standard for new discovery. To put this in perspective, 5 sigma represents a 1 in 1.6 million chance of a fluke, while 6 sigma is about a 1 in 500 million probability. It was an astonishing claim, making headlines worldwide, but the excitement didn't last. It was later revealed that the anomaly was caused by a faulty fiber optic cable and clock synchronization error, not neutrinos defying the laws of physics. So, as with the idea of evolving dark energy, there is still a long road ahead. What's next? Now in its 4th year of the 5-year DESI survey, the project is on track to measure 50 million galaxies and quasars, continuing to provide invaluable data in the quest to understand dark energy. And DESI is far from the only tool we have. In the coming years, new experiments will be conducted. Additional missions will probe deeper into the nature of dark energy, and complementary datasets will become available for analysis. The European Space Agency's Euclid mission at NASA's Nancy Grace Roman Space Telescope will extend measurements across even larger regions of space at higher redshifts, while the Vera C. Rubin Observatory will survey the sky for millions of supernovae, providing the enormous datasets needed to push confidence to the 5 sigma level. I, for one, cannot wait to see what they uncover in the meantime. DESI's latest findings are tantalizing, bringing us to the very edge of a potential revolution in our understanding, both of the standard model of cosmic evolution and the ultimate fate of the universe. So tell me in the comments, what do you think? Will the universe end in a big freeze? Or is a big crunch on the horizon? What kind of ending or perhaps rebirth do you imagine for our cosmos?